Hello everyone, my name is Dian. I work as an engineer at Technology and Engineering Division, Bangkitan Jawa Bali Head Office. I want to present my paper. The title is CFD Modeling to Analyze Pump Shell Covering Percentage on Ketapang CFB Power Plant. So these are this is for the introduction. There are 6 points based this research. The first one is United Nations Framework Convention on Climate Change, or UNFCCC. So Indonesia is committed to contribute in global climate change solution. One of the solution is to reduce greenhouse gas emissions. The second one is COP21 Paris Agreement. The Paris Agreement states that the reduction of greenhouse gas emissions by 29% against business as usual in 2030. The third one is RUPTL 2019 until 2028. So in Indonesia, in 2025, the power must use 20% of renewable energy. Next, the potential of renewable energy. So Indonesia has large potential from renewable energy. It's range around 443 to 108 megawatts. So one of renewable energy source that can be utilized is from biomass. Next, palm kernel shell as biomass. So palm kernel shell is also palm kernel shell also is also used as fuel in biomass power plant in several countries, where foreign countries have imported from Indonesia. And the last one is Ketapang Power Plant covering. So Ketapang Power Plant has implemented by doing the covering test and increased the utilization of the use of this palm kernel shell biomass. So here's for the material and methods. The first one, preparation of palm kernel shell. So covering test conducted on Ketapang CFPP unit number 2 with the percentage of palm kernel shell 3% and 5%. So the plant fuel flow is 11 ton per hour for 10 megawatt load. So for the test, we took 8 hours, and for the co-firing test method, we use direct co-firing. So palm kernel shell and coal, then it the coal yard, and then the mixed process between coal and palm kernel shell done in coal yard with the excavator. Coal palm kernel shell mixing when inside coal bunker through underground hopper. And then the test took 8 hours, 2 hours for stabilizing the mixture in combustion, and 6 hours for data collecting. Palm kernel shell as biomass, so we did laboratorium analysis, 2 points, ultimate and proximate analysis. So you can see the result at the table. So palm kernel shell has lower sulfur, high volatile matter content, and also low ash content. And then the last one, Ketapang Power Plant covering modeling and simulation has been done by using ANSYS software 19.0. So here's for the result and analysis. The first one, we try to compare from the temperature distribution. So 2 points we observe. The first one for the furnace bed plan XZ, and at the furnace exit gas temperature. So we compare experiment and present study by simulation. We got the error below 10%. And then for this, we make further simulation based on the previous one. So we get 3 points of observation: 18 centimeter above the furnace bed plan XZ, middle vertical furnace plan XY, and furnace exit gas temperature bed plan YZ. So with the percentage from 0 until 50% and of palm kernel cell. And the result based on the figures, the head temperature above the furnace bed is more evenly distributed along the horizontal plane than for the non-biomass system. And then the fuel will burn more in wider area. The maximum temperature, which originally occupied a wider area along the middle area of the furnace or vertical plane, was getting smaller along with the increase in biomass percentage. The last one, decrease in furnace temperature was due to differences in the heating value of coal and palm kernel shells. So palm kernel shells has higher high heating value than coal. The next one, CO2 distribution. So we got 2 points. The middle vertical field furnace plan XY and furnace exit gas temperature plan YZ. So based on the simulation, we got, and we can see from the figure, when biomass is added, the mass fraction of CO2, both in the gas exit temperature, furnace exit gas temperature or FEGT, and in the middle of the furnace is higher and spreads evenly compared to the non-biomass system. This indicate this indicates that more complete combustion for the adding of biomass into the system of the furnace. The next is velocity distribution. Actually, we got several data start from 0, 5, 10, 15 until 50% palm kernel cells. And we got from 3 points, 18 centimeter above the furnace bed, 11 meters above the furnace bed, and the last one, 19 meters from above the furnace bed. So based on the figures, we can conclude that when biomass is added, the velocity profile doesn't change much according to z-axis direction. So only 40 and 50% of the biomass that are indications of increasing velocity. Actually, in the area near the wall, both horizontally and vertically, which has the potential to cause erosions. So using higher or too much biomass for firing is not recommended actually for the 40 and 45%. The next one is shear stress distribution. Same with the previous one, we only give 3 simulation, but actually we have several data. Start from 0, 5%, 10% until 50%, but we have 4 points of observation: left side of furnace, front side of furnace, right side of furnace, and last one the back side of furnace. So from the picture, we can conclude that at 0% biomass, the maximum stress occurs in the cyclone area. As the result is same with the 5% until 35%. This area of maximum stress becomes larger as the percentage of biomass is increasing. In other words, in the furnace wall area, the potential for erosion will not occur. At 40 and 45% of the biomass, same like the velocity distribution result, or the maximum stress is shifted to the furnace wall area, so that there is potential for the erosion. And to prevent erosion of the furnace, using large percentage of biomass is not recommended. So next we can determine for biomass percentage optimum. So we use simulation temperature values for 18 centimeter above the furnace bed and in the furnace temperature. So you can see from the table that by adding more percentage of pump kernel shell, it will decrease the temperature value at 18 centimeter above the furnace bed, and also with the temperature value at EGT. And then the last one, we simulate the carbon dioxide mass fraction values. The result, as you can see in the table. So for the conclusion, from the research, we can conclude that first, the maximum temperature which initially occupied wider area along the middle area of the furnace decreases with increasing percentage of biomass. The decrease in furnace temperature is caused by differences in the high heating value of the coal and palm kernel cells, which palm kernel cells has higher high heating value than the coal. Next, when biomass is added, the velocity profile doesn't change much, the z-axis direction, when compared to the 0% biomass or non-biomass system. From the simulation, only at 40 and 45% of biomass, there is an indication of increased velocity. In the area near the wall both horizontally and vertically, which has the potential to cause erosion. So using a large amount or percentage of biomass is not recommended. And last one, we can conclude that the optimum percentage of palm kernel shell biomass used in the Ketapang Power Plant is 30% palm kernel shell. This is caused by the temperature value at 2 points of observation, 18 centimeter above the bed furnace and furnace exit temperature of 30% palm kernel shell, which is not too much different for the 0% results. So the determination of the recommended percentage of this palm kernel shell mixture is also strengthened by high value of mass fraction of carbon dioxide in the 30% palm kernel shell mixtures, which can indicate that combustion in the furnace occurs completely. So that's the conclusion, and this is our references. And then thank you for the time.